Yes.
Okay. Hello. My name is John, and this is my partner Zoya, and we're going to be talking about the research paper that we read, which introduces a distributed machine learning framework and library called Bosen. Okay, so before we start, though, I want to give you an outline about what we're going to talk about. First, we'll give a short introduction about the paper. We'll look at the library. We'll look at who created it and why they created it. And then we'll look at the basic architecture of how the library works. And then we'll give a short crash course of some computations that the library helps simplify. Then after that, we'll look at some synchronization schemes that other libraries use. And then we'll take a look at the one Bosen uses. Then some other optimization methods that the library can use and what happens when servers crash and fault tolerance. And then finally, we'll look at how the library manages communication over the network. And then we'll conclude with some performance of the library and give an overall summary. All right, so the paper that we read is called Manage Communication and Consistency for Fast Data Parallel Iterative Analytics. It's a mouthful. The paper was published in 2015 by some people from Carnegie Mellon, and we'll take a look at who those people were in a bit. And if I had to give a brief summary about the paper, I would say that the paper introduces an optimized parallel and distributed machine learning framework and library. The library is written in both in C++ and in Java. And I actually provided the links to their GitHub pages if you're interested in downloading it. So these are the people that wrote the paper and the framework and library. The main person, though, is, I believe it's pronounced Jin Liang on the top left. He's a PhD student, as so was all the other people in the top row. And the bottom row are professors, and all these people are a part of the sailing lab at Carnegie Mellon. So why did they create this library? Well, I actually think there's a couple reasons. For one, training some of these machine learning models that we're going to take a look at can take days on a single computer. So there has to be a faster way doing this using parallel and distributed techniques. For two, I think maybe at the time of writing of the paper, there was actually a lack of these parallel and distributed frameworks, specifically tailored towards machine learning. I mean, you could use something like MapReduce, but as you see, each framework has its own characteristics and as a consequence has some implications. And lastly, I think the designers thought that the existing libraries and frameworks were lacking in their performance or accuracy. I just mentioned some implications that these frameworks have, and well, some of them are, some of the libraries focus on accuracy of the results, but they're really slow. And then other focus on the opposite. Other frameworks and libraries, they focus on being very fast, but give inaccurate results. So the authors of Bosen tried to meet somewhere in the middle, and we'll see exactly how they did that. All right, so in a traditional architecture, let's just call this a serial architecture. You only have a single node where all your computations are done. And let's say we have a problem to solve which consists of this square, which can be broken up into sections. So in a traditional way, we're going to take a piece of that problem and perform some computations and then solve it. And then we're going to take the next piece of the problem, again, perform some computations. All right, so what are the cons with the serial architecture? Well, for one, it's going to be really slow. As stated before, some of these models could take days to train, but it can be easy to write serial programs. I mean, we all know how to do that. So how do we solve the speed problem? Well, we could use multiple nodes to do our computations. So using Bosen, we're going to need a couple of things. One of those things are a bunch of workers that are going to do the grunt work. We could think of these as our slaves. And the other thing is called the parameter server. And we could kind of think of this as our master. And what the server does, this parameter server does, is it's going to store some shared data that's going to be sent to the workers. And then we'll see in a bit what that data could be. And the parameter server will also have the main problem we're trying to solve. So now it's going to send sections of the problems to the workers, and then the workers are then going to perform these computations. And then each of the workers will send their answers back to the parameter server. All right, so what are the pros of doing it this way? Well, for one, it's going to be a lot faster, and we know that from Amdahl's law. The issue, though, is programming in this parallel manner can be very difficult. Now we're introducing stuff that we have to worry about, such as granularity, fault tolerance, synchronization. But the good thing is that Bosen takes care of all this dirty work for us. Now using Bosen, we could also have multiple parameter servers. And this is good because maybe the communication between worker one on the bottom left and the topmost parameter server is slow. And so by putting another parameter server in between the two, we may be able to increase the communication over the network and create sort of a caching mechanism. So what kind of problems is Bosen trying to solve? Well, one problem is a classification problem using neural networks. For instance, a well-known classification problem is determining what kind of iris a flower is by analyzing its characteristics, such as its septal length, petal width, etc. And ahead of time, we're going to know the answer to some of these rows. And what we're going to do is we're going to call this our training data. And we're also going to have some flowers which we don't know the answer to. And we're going to call that our testing data. And what we want is for our model to correctly determine which kind of iris our flower is based on those characteristics. Then what we're going to do is we're going to take our training data and we're going to feed it into our neural network. And what a neural network is just consists of essentially a series of dot products while adding some weights and some biases, which we don't know the correct values for yet. And the reason why we have these weights and these biases is because maybe the petal length is more important than the petal width. And so what we want to do is we want to give more favor to those characteristics that are more important. Which leads to me some of the stuff that we may want to store on our parameter server. For instance, we may want to store the weights and the biases. All right, so now how does the parameter server communicate these parameters to the workers? Well, one method is called bulk synchronous parallelization, and I'll show you how this one works. The parameter server is going to send those parameters and a part of the problem to each of the workers. And notice these counters at the bottom of each worker, I sub 1, I sub 2, and I sub 3, and they're all set to 0. We're going to take a look at that in a bit. Then each worker is going to perform their series of dot products and computations. And each is going to get an answer, and we're also going to update our counter. Then each of the workers are going to send their answer back to the parameter server. And the server is going to update the parameters based on all the workers' answers. And then the server is going to send the updated parameters to the workers so that they can perform more computations. In reality, though, each worker is not going to be equal. Some are going to be slower than others, and maybe one has slower hardware, or the network is slow, and maybe some other ones are faster. And so let's say worker one finishes very quickly. And then let's say worker three finishes. Let's assume that worker two is really slow. He's our straggler. But I want you to notice something here. Notice the counters. Each part of the problem has been worked on equally, and each of the workers has the most recent parameters. And in other words, each of the counters at the bottom are the same. They're all equal. And just to show you in a different way, notice how each part advances in sync. It may be the case that one of the workers is slow or fast, but they all update together. And that's why this method is called bulk synchronous parallelization. So what are the cons of this method? Well, it's only going to be as fast as the slowest worker. And again, we have that straggler problem. But some good things, though, is it tends to produce the best results. And this is because all the workers have the most up-to-date parameters and guarantees what's called formal convergence. And I find some frameworks online that use this method, that use bulk synchronization parallelization. For instance, there's MapReduce, and there's another popular one called Spark. And if you think about it, it makes sense. If you remember a MapReduce, all the reduced workers have to wait until all the map workers finish before they can start. Another way we can send the parameters is using something called total asynchronous parallelization. So the one before was synchronous, and this one's asynchronous. And just like before, the server is going to send the parameters to the workers. And each one is going to perform some computation. And maybe worker one, uh, uh, maybe this one gets an answer first and sends it back. But when the server receives an answer in the queue, the difference is it's going to immediately update the parameters. And then it's going to immediately send those updated parameters to a new worker to do more computations. And again, it got another answer and it immediately updates the parameters. And now let's assume that worker one is really fast. And so after a while, you're going to see that the middle worker is falling behind. Again, that's a straggler. And is going to receive what's called a stale parameter. All right, again, here's just another way that we could represent the same thing that we saw. And what you're going to see is that the middle worker is falling behind, and then the faster workers, they're just moving on forward. The bad thing about this method is it doesn't guarantee that formal convergence that we talked about, and tends to lead to inaccurate results. But the good thing is it tends to be a lot faster than bulk synchronous parallelization. And I also found some other frameworks that use this method, that use total asynchronous parallelization. These frameworks are not as popular as MapReduce or Spark, or the ones that use bulk synchronous parallelization, but we'll see the first one listed, which is Yahoo's LDA, a little later. And now this is the way Bosen works. So if you remember from the introduction, Bosen tends to pick the middle way. And this method is called bounded staleness parallelization. And so this is how this one works. We're going to initialize a parameter server just like before with the parameters, with the weights and the biases. But now we're going to also include another parameter called the staleness threshold. So this parameter, it has to be a non-negative integer. And what this parameter does is it blocks the workers, the fast workers, by this threshold number so that all the workers sort of work together. So let's say we set this staleness threshold to 2. What are we going to see? What we're going to see is that we're going to block the red worker when it gets too ahead of the slowest worker. So the red worker is going a little fast and it's too ahead of the middle worker, so we're going to block it. And then the same thing again, it gets too ahead of the middle worker and we're going to block it. So one last thing on bounded staleness and synchronous schemes is we can actually transform bounded staleness parallelization into both bulk synchronous parallelization or total asynchronous. I'll show you how. So we're going to transform these. So let's say we set our staleness threshold to 1. So what do you think we're going to get? So we're essentially going to get bulk synchronous parallelization. And now let's set our staleness threshold to infinity. Now what do you think we're going to get? So we're essentially going to get total asynchronous parallelization.
Hello everyone, my name is Zoya and I'm continuing talking about Bosen library and thank you for John for introduce this framework and library. I'm going to talking about other optimization methods which this library uses. Another optimization method that Bosen uses is reducing the amount of data is sent over the network. For example, from 32 bits number to 16 bits number. As you see, let's say that the worker found all of the digits of P number and wants to send it back to the parameter server. So, of course, that would be a huge packet. Instead of that, the worker can send 3.14. The other research papers also say that is a good enough for in these situations. In other words, magnitude of precision are not significant to the overall answer. But furthermore, it increases the performance because we have sent many packets in the same time, and it took to send all the digits of P number. So the other issue is that what happens if the server crashes and then restarts again? So we should recompute everything, and this takes a long time. Well, one method that we can use is we don't keep the checkpoints of the parameters at each iteration. So we would not be worried about writing these parameters to files that can take a long time. So maybe we can finish before the server crashes. Another method is after every update, we save the state of the parameter. So this method, of course, this method takes a longer time, but because we should write it to the, it should be written to the disk, and it takes a long time. But in case if the server crashes, it won't be lose any work. And the way that the Bosen supports it is by saving according to this formula. As you see, T subscript S is a mean time to save the checkpoints of the parameters. T subscript F is mean time to failure, and N is the number of machines. As you see, Bosen is somewhere in the middle. So another issue is that Bosen manage communication. The question is that what happens if we have multiple workers and they send their answers to the parameter server and they wait in a queue at the same time? What happens? So which one should the server prioritize? So now here the Bosen managed communications plays an important role here. And I think that is the best part of the library because they provide a lot of configurations. The first way is we can just assume that one that came first, we were that we did before, first in, first out. Let's say that the blue one came first, so we will take the blue one first. And then we send the updated parameter. Then let's say the red one came. Then the red one came, and then we send the updated parameter to the red one. The other method is randomized. In this method, we can randomly pick one. For example, we pick the third one, the red one first. And then we send the updated parameter to the red one. And then we pick the middle one, that is the yellow one. So we pick the yellow worker next, and so on. The other method is round robin. In this way, every worker gets a fair share. And for example, first we pick the first worker, that is the blue one, and then the updated parameter sent to it. Then we pick the second, that was the yellow one, and lastly the third one, that is the red one. This is round robin. And the interesting one is called magnitude prioritization. In this method, we keep a counter of who is contributing in better work. In other words, we keep a counter of the worker is bringing us to convergence. Let's say that the server takes work from the first worker, that is the blue one, and realize that, wow, this is the one that I was looking for. So the next time that the blue sends work, the blue worker sends work, it will jump to the front of the line. So these are the managed communication role that Bosen plays. That is very important. And as we saw, we have three methods for prioritization. Parameter prioritization. It was first in, first out, round robin, and randomized, and magnitude prioritization. Thank you so much for listening.
All right. So how does this library hold up? Well, the authors tested it by running the library on some commodity hardware, so nothing special. And they ran it against some common machine learning algorithms, some of which we saw, like the neural network. And they also tested on a different configuration. So maybe one setup was just a single computer, another one was a cluster of computers, and they also ran it with and without the managed communication that you just saw. I picked a couple interesting graphs that I thought were somewhat insightful. For instance, in this graph, it shows you how many iterations it took to converge using the different methods. So what you see is that using a single node, it took the least amount of iterations to converge, which is what we would expect because of the formal convergence that we spoke about. And once we introduced the bounded staleness parallelization, it took a significant more amount of iterations to converge. But once we introduced that managed communication, it took almost the same amount of iterations as the single node did. So the problem that I have with this graph, though, is it doesn't tell us how fast it took to execute. So intuition would say that, well, more iterations means more time, but that's not necessarily true. If we introduce more nodes, then we may be able to get the speed up. And this is another graph that I thought was interesting. In this graph, the authors compared their framework and library against Yahoo's LDA. And if you remember, Yahoo's LDA was TAP, total asynchronous. And so you see that it converges much faster than Yahoo, even without any managed communications methods. And this makes sense. Like we just said, Yahoo uses LDA. Yahoo's LDA uses total asynchronous parallelization. And we saw that that method actually has really bad convergence. And so it makes sense. All right, so let's conclude. The big question is, should you care about Bosen? And I would say yes and no. The reason why I say that is because Bosen, it's already a dead project. If you follow the links in the beginning of the presentation to their GitHub page, the last commit was in January of last year, which is a long time ago. I even tried to show you guys a live demo of the library in this presentation, doing some computations, but the Bosen doesn't even build properly. So what that means is the last time they even touched the framework, they left it in a broken state. And the reason why I think it's a dead project is because we're beginning to see a lot of competition in the scene. For instance, we're beginning to see some companies such as Google and Apache. Google has something similar called distributed TensorFlow. It has MapReduce. Apache also has some of their own libraries and frameworks, such as Spark and MLlib. And even Microsoft has one now. And so I don't think a small group of researchers can compete with some of these huge organizations. And I also think that they didn't provide enough evaluation in the library. They only compared it to Yahoo's LDA, and I think of a lot of the graphs, they didn't provide that, they weren't that insightful. I think it would have much better if they provided a graph showing the time it took to complete the same algorithms using, let's say, MapReduce, Bosen, and Yahoo LDA, so that we can see all the different types of methods and how accurate the results were. The one thing I did like about Boson, though, it was that it provided both multiple managed communication methods and multiple synchronization schemes by adjusting the staleness threshold that we saw before. These other libraries, such as MapReduce or Spark, really don't allow that deep amount of customization. And that's good because for some users, maybe speed doesn't matter as much, but they really want accurate results. Or maybe some users really don't care if the answer is a little inaccurate, but they really need an answer right now. And I think that's what Boson does best. Well, thank you for watching our presentation. And if you have any questions, please leave a comment and we'll try to answer as best as we can. Thank you.